The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our first presentation today is post-earthquake repair and structural characterization of a parking structure in Christchurch, New Zealand. Matt Shetler is our speaker, and Matt is here in spite of a little snafu this morning. So Matt is a postgraduate doctoral scholar at University of California, Berkeley. He's been around for quite some time, did his PhD studies at UCSD. So with that, I'm going to introduce Matt.
Good afternoon, everyone, and I'm going to be talking on behalf of my colleagues, Hannah Clark and Jose Restrepo. Hannah is the person responsible for both the design of the parking structure that we're going to talk about, as well as all of the repair work. She works for Howell Fenwick Consultants in New Zealand and couldn't be here to give the presentation herself. Jose Restrepo is a professor at UC San Diego and was the lead PI for an NSF-funded project that looked at damage in precast concrete buildings subjected to the events in Christchurch. And that project was funded by the National Science Foundation, funding from the Network for Earthquake Engineering Simulation, which is funded from the National Science Foundation. And we also had support from the Pacific Earthquake Engineering Research Center in the form of a peer intern who accompanied the team to Christchurch to document damage. David Deutsch is the peer intern from USC. Bob Nigbor is the niece at UCLA personnel who accompanied the expedition. And Robert Fleischman from the University of Arizona is the co-PI of the NSF-funded project. While in Christchurch, we teamed with a researcher, Professor Stefano Pampanin at University of Canterbury, and 3 of his graduate students, Sahin, Umit, and Patricio, helped in the damage documentation that the project undertook. But back to the building. It was completed in 2007. It's a 5-story car park. It's new construction. It has structural walls as the primary lateral force resisting system, and was designed as a nominally ductile building, so ductility factor of 1.25, or if you convert that here, we'd be looking at a force reduction factor of 1.17, with this design base shear coefficient of 0.56 G. The structure has a helical ramp configuration. The traffic is in both directions on each ramp, with parking on the interior and exterior of the building. On the far side from this picture, the building is linked to an adjacent building with a seismically isolated bridge. Not base isolated, simply seismically isolated so that we don't get interaction between the two buildings. The layout of the structural walls along the perimeter in the north-south direction includes 2 walls on either side that I'm calling end or corner walls that are 21 feet long, and there are a total of 10 soldier panels, as Hannah calls them, that are roughly 10 feet long, 10 total. I'm going to focus on the north-south direction because this is the direction where most of the damage accumulated. In the east-west direction, the damage was not nearly as severe. Specified concrete strengths are 4.4 KSI. And the expedition, while we were there, we estimate concrete strengths on the order of 7.6 or 7 KSI using non-destructive testing. Even though it has a large estimated error, we do expect concrete strengths that are much greater than the specified 4 KSI. A little background on the Christchurch events for those who aren't familiar with it. It began in September 2010. With the Darfield Earthquake, a magnitude 7.1 earthquake that was 22 miles from the parking structure that we're talking about. The epicenter is here, shown at the green star, and our structure is here just above downtown Christchurch. That was followed by the Christchurch Earthquake on February 22nd, a magnitude 6.3 earthquake, with an epicenter here, just 5 miles from the parking structure. 2 subsequent aftershocks, both magnitude 6, were located within 6 miles of the parking structure, located here. And if we zoom into the downtown or the city of Christchurch itself, the structure is located here, and 2 GeoNet sensors recorded all of these seismic events. The stations are located 1.2 miles from the parking structure, and with from the peak ground acceleration of these 2 sensors, we can come up with an estimate, just taking the average of the peak ground acceleration from these 2 locations. We have an estimate for the intensity of shaking. I'd also like to point out the duration or the time lag between these events. There's 171, 111, and 193 days between each of these events. So there's enough time to inspect, to plan a repair, to implement the repair, and just then you're hit with another significant aftershock or event. In terms of the peak ground acceleration measured from those stations located 1.2 miles away, we have the first September event followed by a rapid inspection, the February 21st event followed by rapid inspection that highlighted the need for a detailed inspection. And just as that inspection report was being handed to the client, the day of the June event, we were hit with a significant aftershock. That closed the building for two months for repairs. After repairs were completed, another magnitude 6 aftershock occurred on December 22nd that required inspection and additional closure for 1 month. The 5% damped elastic response spectra are shown for the horizontal component and the vertical component in the graphs on the bottom. The design fundamental period for the building in the north-south direction, this is what I'm calling the north-south direction. Here you can see the adjacent building and the bridge linking the 2 structures. I'd like to point out this is the New Zealand design spectra, and you can see demands significantly exceeded the 500-year design basis event. Into the first event, the Darfield Earthquake in September, we had, after a rapid inspection, there was no distinct damage that required repairs. We had no repair cost, despite this being what I'm calling a design level event. If this is our target or our design basis response spectra and demands at the fundamental period of the building or the design period of the building are at or close to or exceed the design acceleration, both in the horizontal and in the vertical direction. But no damage after the Darfield earthquake. I think the surprise in the Christchurch earthquake was that such a large earthquake so close to the downtown area that caused 183 deaths. After a rapid inspection, a more detailed inspection called for further investigation, and the further investigation was removal of cover concrete to expose reinforcement that potentially failed. It was to inspect, to do a more thorough inspection to see what needed replacing exactly. And although the repair costs were zero, the repair strategy was in line, and it was handed to the owner, but it was not implemented because of the subsequent June earthquake. But in general, the damage was cracking of the soldier panels. Those are the more slender walls on the outside of the building, and on the corner walls, 3 of the 4 end walls had minor cracking, and 1 had significant cracking. And the repair strategy was simply to inject the cracks with epoxy or grout and replace the spalled regions with patch. In terms of this event, again, we're at a second design level event for both the horizontal and in terms of the vertical accelerations, we're above the design basis event. The black line here is the New Zealand design code for vertical acceleration. It's specified as 70% of the horizontal component. This is an example of the damage to the connection between the floor diaphragm and the wall. This wall is located here in the northwest corner of the building. and it includes spalled concrete that you can see here that came from there, and cracks in the topping. And again, the inspection report is dated June 13th, the day of the June aftershock. This is a security camera footage of the June aftershock. There's a long introduction while we watch this person park. And unfortunately, you can't see the corner wall. The northwest wall is here. If the camera had been turned just a little bit, maybe we would have seen some of the damage. You won't see any damage. The columns, the beams, and the floors were in general were undamaged. The damage was concentrated primarily in the structural walls in the north-south direction. So again, this is the magnitude 6.3 June aftershock. Magnitude 6 June aftershock. A very, very short duration earthquakes, but with this high vertical component. So this is at the base. That was at the ground floor, and there's one basement level in the parking garage. This is at the roof level. Extremely short. But in general, the diaphragms are intact, with the exception of this corner wall that is out of the picture over here. You can see some of the doors swinging open and some probably some construction crews. Those cars just bounced like crazy. So this June aftershock, there was the rapid inspection that's required. That was followed by a further detailed investigation and repairs that were implemented. Repairs were to actually replace the lowest panels in the soldier panels. 9 out of the 10 soldier panels were replaced, just the bottom section. 1 of the 4 corner walls needed replacing, and the connections between the wall and the floor diaphragm in the one wall, but at 3 locations, had fractured and required drill and bonded dowels with the topping being removed in order to implement those repairs, with the topping being reinstated after. The design period here shown in black, and the measured period, something that was conducted as part of the NSF expedition, was we deployed sensors, I'll go over that in a minute, and monitored and captured what the fundamental period was in the north-south direction. And again, accelerations very close to a third design level event, at least at one of the stations recorded nearby in the horizontal direction, and very extreme vertical accelerations. Like I said, we recorded ambient vibration measurements using accelerometers and a mobile data acquisition system. From the ambient vibration data, we're able to compute elastic fundamental periods for both directions of the structure, as well as an estimated damping ratio of around 3% for the 2 primary modes. These sensors were installed and left overnight or over the weekend, during which we captured 6 low-level aftershocks. And I'd like to point out the period shift here is perhaps due to both the elongation of the structure due to damage, but also we had 2 panels that were missing. While we were there for the expedition, the repairs were underway for the parking structure, so these 2 of the lower panels were actually being repaired. 4 were already repaired, and 4 were in their damaged state. In terms of the damage to the wall-to-floor connection, in the northwest wall, we have kinked dowels, we have fractured rebar, and the repair strategy for these is, first, there was a rapid repair which involved clip angles, bolted angles between the wall and the floor, and those were supplemented with removal of the topping, exposing the fractured bars, removing those, and replacing with doweled in drill and bonded dowels. The flexural damage, this is typical of the soldier panels. It's located here, and in the northwest corner wall where we had the most significant damage, this is the south face, and then the exterior and interior views of that wall where there was the most significant amount of spalling. So this entire lower panel in the soldier panels and the lower panel for this corner wall were all replaced. This is a sample of our damage maps that we compiled as a result of the expedition to Christchurch. With photographic evidence, we're able to reproduce the crack patterns, the spalling that occurred between the spandrels and the wall. This wall here was actually being repaired. It was not, this panel here was not there while we were visiting, and these 2 panels had already been replaced. The repair process was to first prop up the nearby members. then remove the lower panel that was damaged, use the capacity protected, and this is very important, the capacity protected starter bars. These starter bars were designed so that they would not yield in the design event, which really facilitated a rapid repair. Replace the reinforcement, prop up formwork, and put a cast-in-place wall. Here's the repaired wall at the lower left after casting. The walls repaired were 9, they're shown in green, were the 9 soldier panels and 1 end wall. For walls that were not replaced but had significant cracking, the repair strategy was to do grout injection. Another consequence of the precast concrete structure was inter-element pounding. This is shown here between a beam and the wall in the basement. It's located here between a wall and a spandrel beam. And this one may be up for debate. Hannah had suggested that this was compression failure at either end of the wall. This is one of the long, 21-foot-long end walls. But this is at close to mid-height of the wall. And so I suspect that it's perhaps pounding between either the floor level here, the finished floor level here, or the adjacent walls, because this is quite severe spalling for compression failure at such a high elevation, not near the peak moment. And I'd also like to point out that the spalling here between the spalling in the spandrels was occurred most often between in spandrels that were between the stiff end wall and the more slender first interior soldier panel. So these are the locations where compatibility requirements forced demands and caused pounding in these elements. In terms of non-structural elements, again, in regions between the stiff end wall and the more slender soldier panel, we saw pull-out and compression failure of barrier railings that were induced into these walls. And the repair strategy for this is to remove the concrete, check the bolts that they're still intact, and patch the concrete. Hannah's comment is that ideally these elements would not have been tied between the 2 lateral force resisting elements, but barrier loads required this detail. I'm not going to go over the December aftershock, but to say that there was similar damage to the February event, which was here. It was not as extensive, and that it was closed for 1 month for further repairs to do crack injection and to do patching of some spalled concrete. The repair costs for this June aftershock were 2% of the initial cost, and the repair cost for the prior event was at 9.4%. We have some general observations. This structure is an example of anticipated performance from new construction. I'll remind you it was built in 2007, of a nominally ductile structure subjected to repeated seismic demands at or above the design scenario. The facility was under repair and non-operational for 3 months. The total cost for those repairs, for both repair scenarios, was 11.4 of the initial cost, but this does not include direct revenue loss. I'd like to point out that the repairs included conventional materials. The original design strength was reinstated as the design objective. There was not a need to increase the strength beyond what was originally designed for, and that there were 2 catalysts that really facilitated this repair. One was the fact that the gravity load beams were not tied to the structural walls, but were cantilevered out, and this meant that the structural walls were not part of the gravity system. And also that capacity protecting the starter bars really facilitated a rapid repair for the replacement of those walls. Hannah had several comments about her experience, and I'd like to just point out the last one, which is that better education of the clients and the community is needed. There is an expectation of operability post-event, and those are not in line with the performance delivered in the structures that we're currently designing. And she says that the public in Christchurch is slightly better aware of this situation now, but that other communities could benefit from addressing this experience. So I thank you for your time.
The starter bars that you mentioned, were they existing starter bars or new starter bars?
They were existing starter bars. They were from the initial design, and they were capacity protected, meaning the weak link or the fuse was not at the base of the wall, but rather up about a meter. And that's why you saw several flexural cracks, not at the base of the wall, but quite a bit higher. So they were protected.
And how did you connect the new bars to the starter bars?
So let me reiterate that I was not part of the design of the repair. That was all Hannah Clark's responsibility. But the question was simply these are precast. They were initially precast panels, so the starter bars were simply grouted in the precast panel to begin with.
Yes.
So simply casting a new wall around that was enough development. I mean, you saw the additional reinforcement that was included.
So those new bars you had to put new bars in the replacement panel.
Yes.
And how were those bars connected to the existing starter bars?
Yeah.
Just laps?
Lap splice, yeah.
I see.